Hi, my name is Anshul Budraja and this is my Makeup Lab 8. Firstly, this is the email that states that I'm allowed to give a makeup lab and I will not get the standard 30% reduction. Okay, so let's discuss the first circuit, the comparator. So essentially how I wired the comparator up is that the LM741 is connected, the inverting end is connected to 2.5 volts. This is achieved by having two 10 kilo ohm resistors in series, and the non-inverting end is connected to the potentiometer. The comparator essentially checks the voltage at the non-inverting end, and if the voltage at the non-inverting end is higher than the threshold voltage of 2.5 volts, it sets the LED to high. Otherwise, if it's below 2.5 volts, it sets the LED to low. So right now, as you can see, the comparator has the LED set to high. If I move the potentiometer, it goes to low, and then if I turn the potentiometer again, it goes to high. So this is exercise 2, that is deriving the gain of the non-inverting amplifier. So essentially what I've done over here is that I've set V plus equals V minus, and then at the green node over here I've done a nodal analysis, and based on nodal analysis analyzing V plus V naught, I've derived the gain to be 1 plus R2 over R1. And then over here we can see the unity gain amplifier. Now for the unity gain amplifier, we know that V plus is equal to V minus, so there is a gain of 1, that is Vn is equal to V. So this is how I have set up the unity gain amplifier. Essentially the green wire, which is V minus, is plugged into the inverting end. The pot value from the potentiometer goes into the non-inverting end, and so does the yellow wire for V plus. Now after this setup is complete, as we can see over here, we have V out and V in right now, and as I move this up, what we'll see is that beyond a threshold value of around 1.8 volts, V in starts increasing with V out, but as you can see, V out does not reach the 5 volts. Now if I drop this down, what we'll see is that V out stagnated around 1.8 volts and V in continues to drop. This same thing can be seen again over here. Okay, so this is the code I have for processing an Arduino. Essentially in Arduino, I've just set the 4 variables to 0 to initialize them, and then after that it just takes the analog reading from the 4 analog pins and then serial prints it on the monitor. Over here for processing, I've just modified the code from lab 5. Firstly, like I have the actual graph that is being plotted, then the legend that is being created, and then the 4 inputs that are being initialized to like the respective voltage by factoring them by 5 by 12 or okay, so these are my calculations for the integrating op amp. Essentially was pretty similar to the inverting op amp. We just changed out the resistor for a capacitor. So we know that the impedance of the capacitor is given by 1 over j omega c, and then doing a nodal analysis, we get that V out is equal to negative V minus j omega rc, and then once we convert this from the frequency domain to the time domain, we get the correct value. Okay, so this is the inverting amplifier. Essentially these are the calculations for the inverting amplifier that showcase that the gain would be negative R2 over R1, and since for our specific lab we are going to be using a 10 kilo ohm and 1 kilo ohm resistor, the gain is negative 10. So essentially how I've set it up is that I have 2.5 volts constant feeding into the positive side of the amplifier, and then the negative side is connected to a 1 kilo ohm resistor through the potentiometer pot value, and then A0, A1 is getting read by the green and the white wires, and then apart from that we also have another 10 kilo ohm resistor over here that connects to the output. So essentially if we see the input over here, as soon as I increase the V in and V minus values, the V out value drops after the threshold of 2.5 volts is crossed, and as you can see it goes back up. So this proves that the inverting amplifier is functioning correctly. Okay, so this is the circuit for the integrating amplifier. Essentially it's pretty similar to the circuit for the inverting amplifier. Now instead of a 1 kilo ohm resistor, we have a 4.7 kilo ohm resistor. We still have the voltage divider supplying 2.5 volts to the positive end of the amplifier, and now instead of the 10 kilo ohm resistor, we have a capacitor that's going like as a feedback loop from the negative end to the V out. Okay, so this is the output that we're seeing for the integrating op amp. Essentially it's pretty similar to the output we saw for the inverting op amp, except now the difference is that the V out begins to mimic or replicate what V minus is doing when it's below 2.5 volts, as you can see over here, and as soon as it crosses 2.5 volts again it plateaus essentially, as we saw earlier. The reason it mimics the 2.5, like when V minus is below 2.5 volts, is due to the time constant and the nature of the capacitor being charged and discharged. As you can see over here again, it's replicating the behavior of V minus, and as soon as we drop or cross 2.5 volts, it plateaus. Again over here, same thing,